Hello everyone, my name is Dr. Naga Raju, Assistant Professor working as a Assistant Professor in the Department of Computer Science and Engineering, Artificial Intelligence and Machine Learning in Institute of Aeronautical Engineering, Hyderabad. Today I am here to present one of the most important topic again in the Artificial Intelligence and Expert System, which is called as optimal decisions in games. So in the earlier sessions we have discussed most of the search techniques which are related with the heuristics. Means the techniques whatever we have studied, we call it them as the heuristic search techniques. Everywhere our concentration is only to identify the shortest path between the given points. But the algorithms whatever we are going to see in this session, they are not exactly related with such kind of things, means identifying the shortest path. But these algorithms are related with the game playing. Means by playing the game, definitely we know that there will be two players who are going to play the game. So in that cases, how the algorithms will be helpful to the players so that he can complete the task. Okay. So before moving into further concepts, let us try to see some of the topics that we are going to study here today. The first important topic what we are going to discuss is some introduction which is related to optimal decisions in games. Then we are going to see one technique which is called as a Minimax search techniques. Then we are going to see alpha beta pruning, and later we will try to see the constraint satisfaction concept. Right. So coming to the points, if we talk about the overview, as I said that the algorithms what we are going to cover in this session, they are exactly related with the game theory. Okay, means these algorithms can be applicable for the players in order to play the games. So as we know that games has become more fascinating in among the many people. So this compulsory, this can be the notation in the computers that always plays games as given some sort of excitement as long as there are computers. But the thing is here, game playing concepts and game playing theories are not the new concepts. They are already evolved, and they have already started its evaluation from 1950s onwards. The first, we can say that the first person who has started this kind of the game theory kind of things are by the Charles Babbage. Even we call this Charles Babbage as a father of computers, who has actually developed an analytical machine. So this analytical machine he has developed in 19th century, which is used in order to play the chess game. So actually the birth for the game theories has started from this point onwards, we can say. And later on, after Charles Babbage, a person called as Borden in 1953, he also developed a machine which is used to play the tic-tac-toe game. Later, Claude Schumann in 1950, he has described a mechanism which can be useful in playing the chess game. Okay, so this is little bit the history behind the evaluation of this game theory. And come to the overview. Once after that, another one more important person who is called as Alan Turing, he has described one more approach or mechanism, we can say, which is used again on chess playing game itself. Later in 1960s, Arthur Samuel, he also decided to build a very significant program that can be helpful in playing the games. So we can say that he has developed an operational game playing program which is also called as checkers. And let us try to understand what are the main reasons that made the researchers to work on these particular aspects. So as they come to know that, means after some kind of research, they came to know that the games appear to be the good domain in which to explore machine intelligence. As we know that if you want to develop any kind of games related to some machines, definitely we have to feed it with some machine intelligence. Okay, so coming to the point, during the time of their developing the programs, they come to know that they have observed that it is going to provide a structural task, means the development of game programs are going to provide a structural task in which it is very easy to measure the success or failure. And also they came to know that in order to develop such kind of games, there is no required of large amounts of knowledge. And also they believe that these kind of problems, means the game playing problems, are straightforward problems, and which is very easily we can solve them. But actually what happened, it became wrong, means the assumptions whatever they made has become the wrong. Okay, until except the first point, that remaining 2 points we can consider. So what they did is, what they thought is, it is okay even if we are having the limited amount of knowledge, but in order to develop a program which can act intelligently, then definitely you need to require, or you require, large amounts of data or large amounts of knowledge. And even we cannot say that it is a straightforward approach, means the third point is also got failed, means the assumption whatever we have made, that is wrong. Why? Because if you think that the developing of game playing programs are the straightforward approaches and very easily we can decide which player has won and which player has not won, then it is not at all correct. So what happened is, in these things, because of those wrong assumptions, it came the concept called as heuristic search procedure. Means until and unless we implement the same heuristic search procedure, we cannot able to develop such kind of intelligent programs. And we will take one simple example, and we will come to know how this is little bit how it is difficult. If you consider any chess playing game, actually for a chess playing game, the average branching factor will be 35. Average branch factor will be 35, and for each and every player we are going to get an average moves of 50. So as we know that there will be 2 players in chess playing, so each player is having a chance of 50 moves, an average. So what happens, it will become 100 for both the players. So in that case, what happened, you need to examine 35 power of 100 positions to develop such programs. But when you expand this 35 power of 100, you are not going to get a very small number. Definitely it is a very big number. So we cannot give guarantee, that means we cannot say that it is very easy approach. It is going to be very difficult approach to implement this kind of things. Why? Because before making the play, first of all we need to generate a game tree. But generating the game tree for 35 power of 100 positions itself is a very big task. And after that, even if you generate such kind of game tree, traversing among the number of nodes in that game tree, it becomes very difficult. Even for any of the game tree which is having some 16, some depth of 16, it is going to take a lifetime. We can say that even more than 30 years it is going to take to travel around those number of nodes. So in order to overcome these kind of complications that present in developing the game playing programs, so we started introducing the concepts called as heuristic search procedures. And we will try to see how these heuristic search procedures made us to implement the game theory concepts in a very easy way. Let us try to understand one of the search procedure or the search technique which is very popular in game playing, which is called as Minimax search procedure. So this algorithm is completely a recursive algorithm, and even we can say that it is a backtracking algorithm which is used in decision making and game theory. Always it is going to provide some optimal move for each and every player, where the other player also going to act in a optimal way only. Means when you compare it with when you do the variation among two players, those 2 players are going to work, or they are going to play in order to have the optimal result. That's why we can say that those 2 people will play they will try to play the optimal strategies. Okay, so Minimax algorithm, as I mentioned, it is going to be useful in implementing some mechanisms that can be useful in playing the games like chess, tic-tac-toe, and checkers, like that. Okay, so these algorithms, we can say that it is going to compute the minimum decisions for the things. Okay, and coming to the algorithm, in this algorithm specifically there will be only 2 players. One player is called as max and another player is called as min. So both the players they are going to fight it as the opponent player. Okay, as the opponent player, he will try to get the minimum benefit while they get the maximum benefit. Means, for example, if I say Max is trying to play the game, so Max will try to get the maximum benefit, and he will try to make the opponent to get the minimum benefit. So here Max always is going to select the maximum value, and Min is going to select the minimum value. And this Minimax algorithm, it is going to work on the same traditional method which is called as depth first search algorithm. Means, first a depth first search algorithm will be implemented, where we are going to move to the lowest node of the tree, and then we will do the backtracking, and we will continue the process. Okay, with the help of simple example, we will try to see how that really works. Okay, so the algorithm is going to proceed all the way down to the terminal. Just I mentioned, terminal means here, which is nothing but the last point of the tree, and then it will backtrack and it will continue the procedure. That's why, because of this reason, we say that Minimax algorithm is a recursive algorithm, and it is going to implement again internally the backtracking algorithm. Let us try to understand this Minimax search algorithm implementation with a suitable example. So this is the game tree representation I have taken, and in this already I mentioned that it is going to make use of backtracking algorithm. Every time the max player or min player, they are going to select, or they are going to use the best move strategy. They are going to follow the best move strategy, in which what is happening, the max is going to try to maximize the utility. Here utility is nothing but some values. The values what I have mentioned here, -1, 8, 3, -3, -1, these are all called as the utility values. Means the max is going to always select the maximum utility value. Means according to him, it will be considered as a best move. So similar to that one, the min player is going to try, he will try to get the minimum utility value. So we can say that it is a worst move. But for the min player, selecting the minimum value is the best move itself. Okay, so we will try to see how this game tree can be used in order to implement this Minimax search procedure. If you observe this one, you see the first in the in the game playing, the first player will be the max. Means the max is going to start the player, and he is going to try to make use of the maximum utilization of the values. Okay, so that's why we can say that in playing the game, while playing the game, max is going to take the maximum benefit during his start. So that's why the first node, it will be the max node, and the second nodes will be represented as the min. Means these nodes are related to the min player, and next again max, it will go on like that. Okay, so the end, whatever I mentioned here, these will be called as the terminals. And the values I mentioned in this particular point, they are called as utility values. They are the utility values. Okay, by making the help of these utility values, we have to implement the Minimax search procedure, and we have to see how the procedure will keep on going, and how the procedure will make to visit each and every node that present in the game tree. Okay, if you observe in this procedure, what happened just now, I mentioned that it is going to start with the depth first search implementation. So what happens, your search process will start from this point, and directly it will move to this point, means to the terminal. After moving to the terminal, it will try to do the backtracking. Means a backtracking algorithm is going to be implemented. So in this case, what happened, when you move to the background, for D node, we are having two terminals. One terminal value is -1, utility value is -1, and for the other terminal, the utility value is 8. So as this D node belongs to max, it will always try to identify, or it will always try to select the maximum one. So in that case, what happens, the search procedure is going to move in this way. Next, after that, what happened, it is going to update the value of D as 8. Okay, then move to the B node. So what happens, in the B node, initially think that it has selected 8, but 8 is not the correct value here. What happens, so from there, it is going to traverse in this particular fashion. Why? Because among this 8 and -1, so which is going to be selected, -1 will be selected by B. Why? Because B is related to the min player. So min player always try to take the advantage by selecting the minimum value. So in this case, what happened, instead of taking the 8, okay, he is going to take -1. So how it will be minus 1? From here it will move. Means that the minus 1 is not directly selected here. It is going to move in this particular path. And here also there are two terminals for which one terminal value is minus 3 and another terminal value is minus 1. So what happened? E is in the max line. Means E belongs to max player. So he will try to always try to select the maximum value. So minus 1 is going to be selected. So it is minus 1 here. Now you do the comparison. Here what happened for D, the value is 8 and for E the value is minus 1. Now whose turn? Its turn is of B, means the min value, min player. So what the min player will do? He will always try to get the minimum value itself. Means when we compare it with when we compare between 8 and minus 1, we know that minus 1 is the minimum value. So we will select it. Then after, the search will start from here. Okay, search will start from here and we will go in this fashion and then we will come here. So what happened for F mode node, there are two terminals again. One terminal value is 2 and another terminal value is 1. So F node belongs to max. So it will try to take the advantage by selecting the maximum value itself. So that's why the value of F node will becomes 2. Okay, next it will be this one. So what happened in this case for G node, there are again two terminals which is having minus 3 as one value and 4 as another value. So in this case, again it is max player. So he will try to select the maximum value itself. That's why the value for node G is updated with value 4. Now come to C. Why? Because C we didn't select it till now. So what the C is going to do? C is the node belongs to the minimum player. So in this case, what happens? He is going to select always the node value which is having minimum. Okay, so in this case, when you compare between 2 and 4, so 2 is the minimum value. So 2 will be the value for C. And now you come to the A. So what happened here? A belongs to the max. So it is the player max who will try to take the advantage by selecting the maximum value. So what happened in this particular level? This node is having minus 1 and this node is having 2. So as we do the comparison, always we know that the maximum player is going to select 2. That's why we are going to update the value of node A with value 2. Okay, so this is a procedure that generally Minimax search procedure is going to be followed while playing some chess games. While playing some games. But still there are some drawbacks in this Minimax evaluation process. What is that is, we are going to traverse every node. As you have observed during my explanation, I have visited each and every node that present in the game tree. I am not going to leave any of the node. So that means that we are going to traverse all the nodes in the game tree, even though they are the optimal one or not optimal one. So in that case, what happens? We are going to get some computational cost. What is that computational cost? One is the space complexity. The space complexity will be always more. Why? Because we need to represent each and every node in the game tree. Okay, that complete depends upon the depth of the game tree we are going to take. Okay, so obviously it requires definitely a lot of space and also going to be the time complexity. Why? Because we are necessarily or unnecessarily we are going to visit each and every node present in the game tree. That's why definitely it is going to take some time. So when you compare with the computational cost, we are going to have some problem with the space complexity as well as the time complexity. So these are the two problems that has occurred in the Minimax search procedure. So what we are doing is, in order to overcome those problems, we are going to take one more important algorithm which is called as alpha beta pruning algorithm. So we can say that it is a advanced version or the revised version of Minimax search procedure. So in this algorithm, what is happening? We are going to bypass many of the vertices in the game tree. Even though if we are bypassing, still definitely we can find the value of the vertex. Okay. So here what is happening? Alpha beta pruning, it is going to play an important role in reducing the number of nodes. Means if we have observed, means if the algorithm observed that some of the nodes, the path of the nodes is not feasible to us, then simply it is going to ignore them. Okay, that's why we are saying that alpha beta pruning is going to prune. Prune is nothing but eliminate or ignoring some of the nodes present in the game tree, and it is going to select only the nodes or only the path which can help the player. Okay, so we can say that when one chance or option is found at the minimum, it stops assessing a move. Okay, so this method also going to help to improve the search procedure in an effective way. Why? Because there is no concept of course, space complexity we are not going to reduce very much, but time complexity will be reduced more. Okay, how it will happen, we will try to see by taking one simple example. Okay, so coming to the algorithm, in this algorithm we are going to have two things. One is called as alpha and another one is called as a beta. Okay, so we can say that alpha is the max player and beta is the min player. Okay, so alpha by default what happens, actually it is the best value. We can say that it is the highest value. Okay, so this highest value by default we are going to assign with a value called as minus infinity. Means we are going to represent the alpha value by default with the lowest value. Lowest value means the below value. So, but when it comes to beta, beta is going to have the lowest value. The lowest value itself is the best value to the beta. So by default, this beta value we are going to keep it with plus infinity, the highest bound we can say. Okay, so these are the two players we can consider. If it is alpha minimax, we say that max and min are there. But here, as it is alpha beta pruning, in place of max we are going to make use of alpha, and in place of beta in place of min we are going to make use of beta. Okay, so alpha beta values are going to be considered while evaluating or while pruning some of the nodes in the game tree. So always I say that the max player is going to update the value of alpha and the min player is going to update the value of beta. So this algorithm is also going to take the help of the backtracking itself. So during the time of backtracking, the node values will be passed to the upper nodes instead of values of alpha and beta. Okay, so we will only we are going to pass only the alpha beta values to the child nodes. The thing comes is how when we are going to prune the nodes, means whenever a node's alpha value is greater than or equal to beta, then only we can prune that node. Okay. Now try to take this example. Okay, I have taken a very big game tree here so that the entire concept will be easily understood to us. So as I said earlier, every game will start with the max player itself. So first it is max, then min, then max, and again the min. So the lowest one they are called as the terminals with some utility values. Now we will try to observe the procedure how this alpha beta pruning is implemented and how it is going to prune the nodes that present in the game tree. Okay, right, as I mentioned again the same thing, right? First it is going to implement the depth first search. So it is going to start from here and it will come to the lowest point. So means our search procedure, our procedure is going to start from here. So again backtracking will happen. So in this case what happened, this node specifically, the pointer is at this point now. So what happened to this particular node, we need to find out the minimum value. So first what happens, it will be in this way. So the value will be 3 first. The value of this node will be 3. Okay, so what does it mean? What does it mean that I am representing 3? It does not mean that, okay, when you compare it between 3 and 4, the value is, the 3 is minimum value, so that's why I kept here 3. Of course, it may be the reason, but how we have done it, we need to know that. Why? Because there is some sort of procedure in selecting the values for minimum nodes as well as the maximum nodes. So in this case, what happened, the traversing went here, so this is the value 3 and I have mentioned it as a 3. But there is no guarantee that this 3 can be the minimum value until and unless you search in this way. So what happens, whenever I keep this 3 as the node value, that means that this node's value can be either 3 or less than 3. Why? Because it is minimum. Means the value of this particular node always it can be either less than or equal to 3. Means this node already got the value of 3. Okay, so what it will do, it will try to traverse to the other terminal of this node, right, in order to determine is it going, in order to observe whether we are going to get a value which is less than 3. So in that case, what happens, it is going to search in this particular search to this particular terminal. So it came to know that it has observed that the value of this terminal, okay, the value of this terminal is 4. So in this case, what happens when we compare the values 3 and 4, as we know that 3 is the lowest value, means this node is already got the lowest value. So what happens, this particular thing is ignored. Okay, this particular thing is going to be ignored. And coming to the next one. Here, what happens here, we are going to update the value of beta, that will be 3. Okay, and next come here. So in this case, what is happening, initially we are going to keep the alpha value as 3. Of course, we are going to update it again. Then come to this particular node. In this case, what happened, again, we are going to observe these two. The terminal values are 2 and 1. So what happens, we are going to select, okay, the terminal value which is having the lowest. So here 1 is having the lowest value. So we update the value of beta as 1. Why? Because first we update it with 2. Why? Because the traversing will move from towards this side initially. So first we kept it as 2. Okay, then after what happened, we are going to again, means we are not going to fix this 2 as the value of this node. Still we are going to continue our search by seeing the other side of the terminal, other terminal which has given to this node, and we will try to get the minimum value. Means again what happened for this node also, again the value will be either less than or equal to 2. Of course, we got the 2 value from this terminal, but still we are going to search for the other terminal also. Why? Because we may not guarantee. Okay, we may get sometimes the lowest value. So that's why we perform the search here. So what happened, we got the lowest value, less than or equal to 2. So what happened, we are going to update this value and we will keep the value of beta as 1. Okay, and similar to that one, and we got here what happened, here the value of this node is 3 and the value of this node is 1. Now come to here. This is the max. So we need to update the value of this max node. So always we know that the max node is going to select the maximum value. So in this case, what happens, when you do the comparison, this node is having 3 value and this node is having 1. So obviously the value of this node will be 3. The same way what happens in this case also, it will happen the same thing. So what happened, right? We are going to come in this particular direction. Okay, first we will keep the beta value as 3 and we will see whether that value is going to be updated or not, and come to this particular point. Here we are going to see this particular node, so 7. So this, what we think is 7 will become the value of this particular node, and again still we are going to search this one. Why? Because we sometimes we may get the lowest value. So actually, but here 8 is there. So we can come to know that this is not the lowest value. So what we do is we will keep the value of beta as 7 itself. And for this one also, we are going to keep the value of node as 9. So what happens, the beta value will become 9. So when you do the comparison in between these two, so we need to take the value of this alpha. What is this max value? So 7 is there and 9 is there. So max value na, so it is going to select the maximum value itself. So the alpha value may be 9 here. Now come to this particular point. Here it is the min value. Previously we got the min value, or means the value of this min node as 3. But we don't know. But that's why we are searching even in this particular thing also. But what happened here, we got the value of 9. But 9 is not the minimum value when it compared with the already existing beta value 3. So that's why what we are doing, we are simply going to ignore this particular branch of the tree. Okay, so this process we are going to continue further. So what happens here, it will become 2. The beta value will become 2 here. It will become 1. This will become 9. And this is going to become 13. Okay, so here the beta value will be 1, beta value will be 9, and beta value will be 13. So what happens, you have to come up. So in this case, what happens? This node belongs to the maximum value. Means it is going to select the maximum value. So the alpha value will becomes 2. So the value of this node is 2 again. The value of this node will be 30. So again, this is the minimum node. So the value of beta will becomes 2. Why? Because when we do the comparison of 2 and 30. Now what happened here? The min value is 3 and min value is 2. Okay, at this particular end, what happens? It is going to select the maximum value. Why? Because this node belongs to the player max. So when we do the comparison between 3 and 2, we know that 3 is the maximum value. So it is going to update its alpha value from minus infinity to 3. Okay, when it is the case, so what happened here? Again, we are going to ignore this particular part. Every time, right? Every time you make the observations, we are going to ignore some of the paths. So in this case, what happened? We ignored this one. Here we ignored this. We ignored this one, we ignored this, and we ignored this. But finally, what happened? In this particular case, okay, we ignored this, and at the end, we ignored this entire branch. This is the process called as pruning process. So where we are going to take the values of alpha and beta, and we will keep on updating the values, the alpha beta values, and during that time, we are going to prune the nodes. Okay, we are going to prune the nodes in the game tree. So what happens during the game playing process? We can say that it's not necessary to traverse among all the nodes that present in the game tree. Because of that, we can say that the time complexity is going to be reduced to a greater extent when we compare with Minimax search algorithm. So that is all about the two important techniques related to game playing. One is called as Minimax search algorithm and another one is alpha beta pruning. And come to the other concept of game theory, which is called as constraint satisfaction. Okay, so the name itself is saying that it is a constraint satisfaction. Means we are going to continue our game playing once we met the conditions that are given to that particular step. Okay, that's why we say that it is called as constraint satisfaction. Means we are going to continue our game playing process based upon the satisfaction of the conditions given to us. Okay, so many problems we can say that in artificial intelligence, they are viewed as the problems of constraint satisfaction itself. Okay, I will take one simple example. Okay, during this one, how can we say that it is constraint satisfaction? Okay, how can we say that constraint satisfaction? For example, if you take the Sudoku game. So during Sudoku game, you know that each and every box is going to have 9 sub boxes. Okay, 9 sub boxes. We need to fill them with numbers from 1 to 9. Whenever you are trying to keep one number in a particular cell, you have to check that the horizontal and vertical position, mean diagonals, there should not be 1 again. So what is happening there? You are keeping some kind of conditions. Means if you want to keep some number 1 in particular box, you have to see that for example, if this is the box, here I want to keep 1. Okay, think that this is one of the part of the Sudoku. So what happens here? I want to keep 1. But in this case, what I have to do? Before keeping 1, some constraints need to be satisfied. So what are those constraints? So here in this particular line and in this particular line and in this particular one, there should not be 1. 1 should not be repeated. Okay, so what happening here? The Sudoku game itself is having some constraint satisfaction rules. Until and unless you satisfy those constraints, these 3 constraints, you should not supposed to keep 1 here. Okay, like this it will be. So we can say that it is a problem in which the goal is to discover some problem states that satisfies a given set of constraints. So the example for these kind of constraint satisfaction problems are crypto arithmetic puzzles. Okay, we can say that it is a Sudoku game problem, and it is also, we can say that, color filling problem. In this session, we will try to see this color filling problem also. Okay, use of constraint satisfaction. How it will be? See, the main advantage of viewing this problem as one of the constraint satisfaction, because it is going to reduce the amount of search. The main advantage is it is going to reduce the amount of search. Why? Because unnecessarily we are not going to perform the search activity until and unless that the given conditions are met, then only we will continue our search process. Otherwise, we are going to stop here itself. And coming to the algorithm and the procedure, algorithm or the procedure, we can say that every constraint satisfaction problem is going to be represented by using three different components, which is called as V, second one is G, and the third one is C. So what is V? V is a set of variables, just like we can mention it as V1, V2, V3, like that up to Vn. So Vn means here all these are the finite sets. Okay, they are all the finite sets. So V is represented as a set of variables, and D is represented as set of domains, set of domain for each and every variable here, and C is the set of constraints that specify the allowable combination of the values. So how we are going to frame these constraints means there is a specific syntax we have to follow. Ci equal to scope comma relation. Means whatever the constraints you want to apply to that particular situation or to that particular step, you need to frame it earlier. Okay, so how can you do it? Means by keeping the scope and relation in this particular fashion, you can do it. We will take one example and we will try to understand how that will happen. Okay, so scope is a set of variables that participate in the constraints, and relation defines the values that variables can take. Okay, so how it will be, we will see. Consider three constraints. One is called as C1, C2 and C3, and two variables V1 and V2 for each constraint. Each constraint means for C1 there will be two variables. One variable is called as V1 and another variable is called as V2. And we are also taking that for this V1. Okay, for this V1 variable there is a domain called as A, and for V2 there is a domain called as B. So what is the constraints we are framing here? You see, first it is in the constraint the scope. Who is involving in this? V1 and V2 are involving this in this constraint. So what is the relation you are going to give? Every time it should not be same. Means the V1 value should not be same with V2. This is the first constraint I am framing. The same constraint I can represent in another way also. That is, first I am keeping the scope, saying it as V1 and V2 are the variables which are participating in this, and we are representing those variables as A1 domain and A domain and B domain. Okay, so what does it mean? It means is for A there will be two values. For example, think that 1 and 2 values are there, and for B there are again two more values which is called as 2 and 4. So what we have to do is we need to frame the constraints. We need to frame the constraints based upon the conditions given here. So what happens in that case, right? If you consider the scope, first scope is who is participating. So I said that V1 and V2 are participating. And what about the relation? What about the relation means here from A I can take value 1 and from B I can take value 2. And the second one, from A I can take the value 2 and from B I can take the value of 4. And from A I can take the value of 1 and from B I can take the value of 4. But I should not supposed to take value 2 from A and value 2 from B. This is not allowed. Why it is not allowed means there is a specific condition we mentioned here in the constraint itself. What is that? V1 value should not be equal to V2. Okay, so in this case what is happening? There are only these particular things that are possible. 1, 2, 2, 4 and 1, 4. That's it. There will be no 2, 2 here. We will try to take this example and we will understand how this implementation, constraint satisfaction implementation will be there. So this is the graph taken by us. This is a graph. So what is the main intention of this graph is, this graph is related to color filling game. It is a color filling game. So how many circles are given? 4 circles are given to us. So in these 4 circles, what we have to do is we need to fill up the colors. Okay, so what are the variables? 1, 2, 3, 4 are the variables here. Means totally 4 variables we are having. And for each and every variable, domain values. So what are the domain values? Red, green and blue. Means for variable 1, red, green, blue will be there. For variable 2 again red, green, blue. For 3 and 4 also red, green and blue. So what you have to do is our goal means our game is we need to fill up these circles with some colors. But during the time of filling, some constraints need to be satisfied. So what are those constraints? 1 should not be equal to 2. 1 should not be equal to 2 means here you come to here. Means whatever the color you are keeping in this one, filling in this one circle should not be same with the color filling in B. Means for example, if I fill the color red here, I should not supposed to go for red in this place. And even I should not supposed to go red in this place. I should not supposed to go and fill this circle with red. These are the conditions given to me. That means that no two circles should have the same color. Okay, it will be like this. So these are the constraints given to us. So if we start the game from the initial domain, what happens? For each and every variable, we are having 3 possibilities. Why? Because it is an initial state. Means circle 1 you can fill it with red, green and blue. Circle 2 also, 3 and 4 also you can fill it with red, green and blue. That's why we have mentioned here RGB, RGB, RGB and RGB. But come to this one. Means we have started filling the circles. So what I have done is, first I have filled the circle with red. Okay, I will try to remove this one so that there will not be no confusion here. Okay, so first what I have done, I have filled the circle 1 with red color. That means that now this circle is with red color. So in that case, what happens? The other circle is having only 2 chances. Means the second circle, this second circle is having only 2 chances. One is I can fill it with green or I can fill it with blue. Similar to that, one for 3 and 4 also, there are only 2 possibilities for me. Why? Because red is already taken here. So I should not supposed to take red for 3 and 4. So the same possibilities which we have taken for 2, the same possibilities are there for 3 and 4. That's why we mentioned G, B, G, B and G, B here. Next, what we have done, we have filled the second circle with green. Okay, now means here we are having the color. This circle is filled with green. I should take. Why? Because I am not going to restrict, I am not going to remove this constraint. What is that constraint? You should not supposed to use same color. Here there is red and here there is green. There is no problem in this case. So what happened? In the second circle, I have filled with the green color. So coming to the third one, what happens for this circle 3? There are only 2 possibilities. What is that? I can fill this with green or I can fill it with blue. I can fill it with blue. That's why I mentioned as G, B. But 4, it is not the case. Why? Because 4 is having the connectivity with circle 1 and circle 2. In circle 1, we are having red. That means that you should not supposed to fill this circle with red. It is having connection with circle B also. Already circle B is filled with green color. So I should not supposed to fill this circle 4 with green color. Means red is not allowed and green is not allowed. So what is the only one color left? Blue. So what I can do? I can fill that one with a blue color. So this is a possibility. And coming to this one, third node, okay, third circle, I can say third circle I have filled with a color blue. Okay, this is allowed only. Only you should not supposed to fill this with a red color. Green color also you can take and you can also take blue color. But think that we have taken blue color. So what happens when we take the blue color? That means that for this particular one, there is only one possibility. Again, that blue you have to take. Why? Because red you should not supposed to take. Why? Because red is already there. Green you should not supposed to take. Why? Because green is already there. And blue you have to take. That is only one chance. Why? Because red is not allowed and green is not allowed. But what happened here? Already you filled this circle 3 with blue color itself. So what is happening here? We are reaching to some kind of dead end, some dead point. Means we are not going to solve this problem, this game. So what happens? We will perform some backtracking, which is called as intelligent backtracking. Okay. In this intelligent backtracking, what we are doing is, first it is already there with red, and second it is already there with green. And now instead of taking this circle, means instead of filling this circle with blue, I am going to fill this circle with green. So in that case, what happens? Happily, we can fill this circle 4 with the blue color. So what happened? We could able to reach to some goal point, or we can say that we have completed the game. Okay, so this is how the color filling games are generally played by implementing the concept called as constraint satisfaction. Coming to the other concept what we are going to study now, which is called as means ends analysis. So far we have presented a collection of such strategies that can reason either forward or backward. Means even if you observe the heuristic search techniques whatever we have implemented, either they have followed the forward search procedure or they have followed the backward search procedure. But till now we didn't see that the problems are the situations in which you can implement both the forward search and backward search at the same time. So our motto by working with this means ends analysis is we need to solve the problem by implementing the forward reasoning and backward reasoning at the same time. Okay, so generally where it happens is we are going to use this kind of things, means we are going to consider the problems, right, where we can say that most of the parts, means major parts of the problems first we are going to take, and then we will go back and we will try to solve the smaller problem. So we can say that it is a kind of divide and rule. Okay, so in this case what happens, we are going to select one big problem, then we will divide it into multiple parts and we will try to solve those individual parts first, and then we will come back to the main one. Okay, still we will try to see how this means end analysis will work with a suitable example. Okay, so this analysis we can say that it is going to concentrate around the detection of differences between the current state and the goal state. So the kind of problem whatever we are going to deal in this case, it is entirely different with the problems what we have seen earlier. Okay, so every time what happens here in this case, the initial state is given to you and the goal state is also given to you. So what you have to do is you need to identify the differences between the initial state and the goal state. Okay, so once the difference is identified, and if you come to know that the difference between those 2 points are very large, so your concept is you need to reduce the distance. So in order to reduce the distance, you are going to give some list of operators. By taking the help of those operators, you have to keep on applying them. And you should supposed to reduce the distance. But what happens during the time of application of these operators, you should not supposed to directly apply that operator to the current state. So in that case what happens, again some sub problems are going to come. So what you have to do, you need to overcome that sub problems first, and then you have to come to the current state application. Okay. So the kind of backward chaining in which operators are selected and the sub goals are set up to establish the preconditions, generally we call this procedure as operator subgoaling. But what happens is the operator, we may not guarantee that it is going to produce exactly the goal state what we are looking for. Just now I mentioned, right, whenever you try to apply a operator to a specific current state, you may not get it. So in that case what happens, again some sub problems are going to come. Means when you are trying to solve a specific problem, some other problems are going to raise. So you have to clear up those sub problems, and then you have to come back. Okay, so this is a strategy, this is a procedure that generally happens in this means end analysis. Okay, I will try to take one example which is there in the textbook. So according to the textbook, what happened, there is a robot is deployed. In order to perform the household activities. So what is the task given to this robot is, in a particular room, for example, think that some room A is there. In this particular room, there is one desk. Okay, there is one desk, and this desk is having two objects, object 1 and object 2. So what is the task given to this robot is, the robot has to shift this entire desk along with the objects from room A to room B. Okay, so in this case what is happening, this is the initial problem statement given to us. So what we have to do is we need to, we can say that this is the initial state. This is the initial state and this is the goal state what we have. So what we are doing, we are trying to identify, means initially when this kind of problem statement is given to us, according to means ends analysis, we are going to identify the difference between these two. So obviously we are coming to know that we can see that there is a lot of difference between these 2 points, initial point and the goal point. So what you have to do is you need to reduce this difference. There is a difference, that difference we need to reduce it by applying the appropriate operator. Okay, the operators list can be anything, right? It can be push, it can be a walk, it can be pick. Okay, so means before implementing or before trying to solve this problem, some list of operators are given to you. By using those operators and by applying those operators in a specific sequence, means systematically you have to reduce the difference between the given initial point and the expected goal point. Okay, but if the difference is chosen correctly and if the operator is really effective, then we can say that we have reduced the difference. Okay, now then what we do, we will try to implement the mean sense analysis in the recursive way. How it will be, right? We will see that. MEA is realized to going to depend on the set of rules. Okay, why? Because when, if it is the application of the operator, that means that there are some set of rules that need to be fulfilled. Okay, so that's why we are saying that we are going to completely relay. Means here the mean end analysis is going to completely relay on the set of rules that can transform one problem state into another state. Okay, so these rules are going to be usually not presented with a complete state description. Means there is no concept of state description. So whatever the problems are arising, those problems we have to keep on solving them. Okay, so how the rules are have been placed means there will be 2 things. One is the left hand side will be there and another one is the right hand side. So the left hand side, what it is doing, it is trying to describe the conditions which need to be met by that current state. Okay, and also we can say that which rules they are applicable to that particular state, that particular current state. Okay, and the right hand side, it is going to describe. As I mentioned, this rule is going to have 2 parts. One is left hand part and another one is right hand part. And the right hand part, it is going to describe the aspects of the problem state. So that we can say that it has been changed. It is going to be changed based upon the application of the rules. So in order to solve these problems, a separate data structure which is called as a difference table indexes. Okay, this is going to be given to you. So what you have to do, you have to keep on applying the operators given in this one. And your ultimate goal is you have to reduce the difference between the given initial point and the expected goal point. Okay, what is the strategy? So if you observe this one, the strategy will be like this. You see, our primary thing is we need to achieve the goal, that is G from state S. Means the state given to us is S and we need to go to G. Okay, so what we have to do, we need to identify the operators. So what is the operators we are having? Some O1, O2, O3, OI up to OK. The finite set of operators will be given. So whenever you apply this kind of operators, what happens? You are going to move from a state S, okay, from a state S to S to S dash. Okay, means directly if you apply the operator, you are not going to move to the goal state what we are expecting. But what happens here internally, there will be some more sub problems will come. Those sub problems we need to solve it. Okay. And this is the algorithm given to us, mean end analysis algorithm. So I will try to explain this algorithm in a simplified way by taking one simple example, which I have collected from the internet sources. So this is an example what we are taking. So in this case, what happened? 2 states are given to us. One is the initial state and the goal state. So what are the available operators? Means what are the operators given to us is, one is move operator, delete operator and expand operator. So you have to apply these operators to the situations. Okay, means appropriate selection of the operators is required, and by applying them you have to move or you have to reduce the difference. We can say you have to reduce the difference between these 2 states. First of all, we will try to understand what is the difference that present here. So in the initial state, there are 3 shapes given to us. One is the filled circle, second one is the circle, big circle, and another one is the diamond symbol or some square symbol. So what happened? The goal state given to us means we need to move. We have to move to this particular state. So what is the difference we are finding in this one? In the gold state, there is no field circle. That is the first difference. So we can say that first one is no field circle. Okay, so what is the second difference? Okay, circle and square shape, or we can say circle or some square are separated. And the third difference is also there. What is the difference? In the initial state, the size of the square is little bit small, but when you observe it in the gold state, it is very big. So what you have to do? You have to expand the size of the square. You have to expand the size of the square. So how many sub problems we got? There are 3 sub problems we got. Whenever we keep on applying the appropriate operator to this particular thing, we could able to reduce these things. We can say that these are the 3 differences between these 2 states. So how these differences can be reduced? By selecting and applying the appropriate operator to that particular one. So first, what we have to apply? What operator we need to apply? So in this case, what happened in step number 1? First, we are evaluating the initial state. And in step number 2, we have selected the delete operator. So what does the delete operator will do? It is going to delete the filled circle from the given state. So what happened after performing the delete operator? This is the state you got. Okay, that means that we have selected the appropriate operator itself in this particular case. Why? Because we have observed that in the gold state, there is no filled circle. So some sort of difference has been reduced between the given initial state and the gold state. And coming to the next one. In the step number 3, what we have done is we have applied the move operator. Why? Because we have observed that the square is not inside the circle, but it is outside the circle. So what I have done, first we have applied the delete operator. Then we applied the move operator so that we can separate this filled square and with this circle. So once it is done, we came to this particular position. But what is our third difference we identified? That the shape of the square. In the initial state, the shape of the square is little bit small. But in the gold state, the size of this shape is a little bit high. So what is the appropriate operator we can apply here? It is expand operator. So what we are doing at the end, we are applying the expand operator, and we will we are increasing the size of this square. So that means that we have maximum extent we have reduced the differences between the given initial state and the goal state. Like this, means ends analysis are going to be applicable. They are going to be applied like this. Okay, coming to the references point of view. These are the 2 references that I have considered during the preparation of this content. So this is up to today's session, and in the next session we will try to come up with the other important topics of artificial intelligence. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.